Welcome to the third plenary of the Fifth International Congress of Mathematical Modeling. Now it's turn of Nicole Halpern to give us a talk. She is an ISE physicist and an adjunct assistant professor of physics at IPST at the University of Maryland. She makes revisions in the 19th thermodynamics for the 21st century using the mathematical toolkit of quantum information. She applies QI thermodynamics as a lens through which to view the rest of science, gaining new perspectives on atomic, molecular, and optical physics, considered matter, chemistry, high-energy physics, and biophysics. Halpern calls this research quantum steampunk, after the steampunk genre of art and literature that juxtapose Victorian settings with futuristic technologies. She received her doctorate in physics from Caltech in 2018. Halpern's thesis won the International ILJA Prize for a thermodynamics dissertation. She is continuing with her post as an ITMP postdoctoral fellow at Harvard University until summer of 2021. You are welcome. Please go ahead with your presentation.
Thank you for the introduction, and thanks very much to the organizers for the invitation to present this talk. So as you heard, I usually deal with quantum thermodynamics and the study of energy, but this talk is going to be more focused on quantum information. It starts with how I am very fond of probability distributions. So how come? Because they describe so much of our world. For instance, I recently lived in the Boston area, and the dominant weather pattern in the Boston area on any given day is a very, very random variable. Let's call it X. There are various possible values of X for the different types of weather patterns there could be. For instance, X1 could be rainy, X2 could be sunny, and so on. And there's some probability distribution associated with these possible values. And that probability distribution sometimes feels like it's pretty close to uniform. Another example comes to us from classical statistical mechanics. Suppose that we have a classical everyday system of many, many particles, such as a gas in a box. These particles are in some microstate. That is, all of their positions and momenta have some particular values. That number of particles is very, very large. It's Avogadro's number. It's too large for us to actually know what all the positions and momenta are. So we can't actually know the precise microstate of this system. Instead, we list all the possible microstates of the system, and we ascribe a probability density to the space of microstates, which we call phase space. So this P denotes the probability that particle 1 is in position x11, particle 2 is in position x12, and so on. And particle 1 has momentum p11, while particle 2 has momentum p12, and so on. This probability density we represent on this cartoon of phase space. The phase space is a many-dimensional space in which each one of the axes is labeled by one of the arguments of that probability density. And that probability density forms some blob on phase space. It represents our ignorance about the exact state of the system. So in this way, we can represent the state of a classical statistical mechanical system with a probability distribution. This is very commonly done. And that fact, though, might lead us to ask, can we represent the state of a quantum system with a probability distribution? That is, can we write down some function p or p tilde that depends on a quantum state row and has some arguments, such that we can use this function to calculate all the things with which we can, or all the things that we can calculate using quantum theory. So probabilities of possible outcomes of measurements and average values or expectation values that come out of measurements. So can we represent a quantum state with just one probability distribution? The answer is almost, but not quite. To understand why, we should review the axioms of probability theory. I'll present them for some discrete probability distribution for simplicity and for relevance to the quantum systems I'll talk about shortly. Each probability in a distribution is real. It's at least 0. The probabilities are normalized to 1, and they sum in certain ways. The probability that some random variable has a value in some set equals the sum of the corresponding probabilities. We need to relax at least one axiom of probability theory in order to represent a quantum state with a distribution. If we relax different axioms and make other parameterization choices, we get different quasi-probability representations of a quantum state. I'll denote quasi-probabilities by ~p. Most quasi-probabilities have the property that if you marginalize over all of these arguments except for one, then you get back an ordinary probability. So here we have our quasi-probability, we're marginalizing it over all of the arguments except for the jth, and we get an ordinary probability. The probability that if I prepare a quantum system, maybe an electron, in the state row, and then I perform some measurements, then I'll get the jth outcome. These quasi-probability distributions have been useful historically in quantum optics, the study of light, the foundations of quantum theory, and a few other subfields. My favorite quasi-probability distribution is called the Kirkwood-Dirac quasi-probability distribution. It was defined in 1933 by John Kirkwood and independently by Paul Dirac in 1945. Then it was basically forgotten about, mostly, for many decades. But over the past few years, it's experienced a resurgence because it's been shown to be useful in many subfields of quantum theory. It has some nice properties. For instance, it's defined straightforwardly for continuous and discrete systems. It has some other properties I'll talk about later. And it has these many applications across subfields of quantum physics. Here's where I'd like to go in the rest of this talk. First, I understand that a number of people here might not be familiar with quantum theory, so I'll provide some background about quantum information theory. Then I'll define this quasi-probability and talk about some of its properties. I'll show how it can be useful in quantum metrology, the study of how we can use quantum systems to measure properties of the world. And then I'll talk about opportunities for future work. I'll present some background on quantum information theory. It might be too much for some people and too little for others, but hopefully there's some kind of medium here. The basic object in quantum information theory is the qubit. The qubit is the basic unit of quantum information. It's the quantum analog of a bit, which is one of two possible values, such as left or right, or 0 or 1. A qubit can be encoded in a physical system that obeys the laws of quantum theory, for instance, an electron or an atom. And a qubit is associated with a two-dimensional Hilbert space over the complex numbers. The quantum state of a qubit is represented by a vector in this Hilbert space. And the vector is normalized to 1. We can represent the state of a qubit with this symbol, which we call ket psi. You can think of it as a column vector of 2 elements. Also, we can represent this quantum state by this kind of doubled symbol. If this ket psi over here represents a column vector, then this inverted symbol represents the conjugate transpose. So you can think of this whole symbol as an outer product or a 2x2 matrix. We represent the state of a qubit with points on or in the sphere, or more precisely, an arrow that extends from the center of the sphere all the way to the surface of the sphere. So this arrow pointing upward represents the quantum analog of the 0 bit that we saw earlier, and it's represented by this column vector as well. This downward pointing arrow represents the quantum analog of the 1 bit that we saw earlier. It's also represented by this two element vector. And a quantum system can be in a state that's any superposition of 0 and 1. For instance, we could call the amplitudes of the elements of this vector C0 and C1. Those amplitudes are complex numbers that are normalized to 1. That's the state of a quantum system. A quantum system can have also observables or measurable properties. Examples of observables are position and momentum. An observable is represented mathematically by a Hermitian operator defined on the Hilbert space of the system. For instance, the observable A can be represented in terms of this eigendecomposition. So again, this is an outer product that you can think of as a 2x2 matrix. A reason why quantum physics differs from the physics of our everyday world is that quantum observables and other properties of quantum systems are represented by these operators that can fail to commute with each other. Now that we've seen a little bit of an introduction to quantum information theory, let's use some of that formalism in defining my favorite quasi-probability distribution. This quasi-probability distribution can be used to represent a quantum state rho, again, a 2x2 matrix. This state is of some quantum system, say a qubit. That qubit has a Hilbert space that has bases. Let's call two of them A and F. We can think of these bases as eigenbases of observables, Hermitian operators. The Kirkwood-Dirac quasi-probability for this state associated with these two bases is the trace of this product. And this product contains the quantum states, the outer products of an A eigenbasis element, and the outer product of an F eigenbasis element. So for those of you who are familiar with quantum theory, you'll notice that this looks very similar to a probability, but it's not quite one. This quasi-probability has some very useful properties and also very intriguing properties, but it can contain negative values, unlike ordinary probabilities. And if you're interested in an example, then you can check out the appendix of this paper, which is kind of a foundational paper about the Kirkwood-Dirac quasi-probability. And these negative values relate to how quantum systems have wave-like properties that can interfere with each other. Also, the Kirkwood-Dirac quasi-probability can have non-real values, very differently from a probability distribution. An example is also in this paper. For instance, this is a quasi-probability representation of a qubit with respect to certain bases. And here, all of the elements of the distribution are non-real. These negative and non-real values we call non-classical values because they're not accessible to the probability distributions that we said earlier in the talk describe classical systems. This quasi-probability distribution is not only theoretically nice to deal with, but it's also measurable in experiments. We can measure it using weak measurements, which don't disturb the quantum system very much. You might have heard of Heisenberg's uncertainty principle, which indicates that whenever we measure a quantum system, we disturb it. But we can soften our measurement so it doesn't harm the system too much. Our quasi-probability is defined in terms of two bases. And we said that these bases could be eigenbases of some observables. If the observables commute with each other, then they automatically share an eigenbasis. If each of the bases in the quasi-probability is that shared eigenbasis, then the quasi-probability reduces to a simple probability. Here again is the definition of the Kirkwood-Dirac quasi-probability. If we set F equal to A, then the quasi-probability simplifies to this trace, which is the probability that if we prepare the quantum state rho and we measure the observable big A, then we'll obtain the outcome little a. Now that we've had an introduction to the Kirkwood-Dirac quasi-probability, let's see how it can be useful in quantum metrology, the study of how well we can measure things. A very common task in quantum metrology is called parameter estimation. Suppose that we've been building some quantum device, say a quantum computer, that has to implement some quantum logic gate. That logic gate we would build as accurately as possible, but we are poor, imperfect human engineers. So that gate isn't going to be implemented exactly as it's supposed to be. And this gate could perform some operation that depends on some parameter theta. We've tried to make this gate use the right parameter, but it's going to be a little bit off in reality. And we would like to measure what parameter theta is actually used by this gate. I'm going to set the origin of my number line such that the expected value of this parameter is 0. I'm also going to assume that this gate acts as an exponential that is generated by a Hermitian operator A. And many, many, many quantum operations act in this fashion. Again, we'd like to estimate this parameter. How do we do that? We prepare some quantum state, maybe a photon. We send it into our gate. The gate imprints the parameter on our quantum state. We measure the quantum state and we get some outcome. Let's call it B. That's distributed according to some probability distribution that depends on the parameter. From that outcome, we infer information about the parameter's value. How do we quantify the amount of information that we've learned about the parameter? Our quantification is called the Fisher information, denoted by I of theta. Loosely speaking, the Fisher information is the average amount of information about the parameter that we learn per trial. Here's how I think of the definition. It's maybe not the best way to think about the definition, but it's the way I think of it. Suppose that our measurement yields outcome B, and we'd like to know how many bits of information we gain. Well, if there's some random event, we don't know which particular instance of it is going to happen, but we know the probabilities of the possible outcomes. We know that, and we suddenly learn that one particular outcome happens, B, then the extent to which we're surprised by that event depends on the probability that the event had. So the surprisal, or the amount of information we learn, is defined as the negative of the log of the probability of the outcome. This definition we can perform a sanity check on. It makes sense when the outcome is perfectly known in advance. If the outcome is determined in advance, then only that outcome has a non-zero probability. That probability is 1. The negative of the log of 1 is 0. And indeed, we gain 0 bits of information when we already know what's going to happen. Now, how sensitive is this amount of information gained from the outcome to small changes in the parameter theta we want to learn about? The answer to that question is given by a derivative. We're not interested in only one particular outcome. We're going to perform many, many trials. We'll get many, many outcomes. And so we want to average over these outcomes. Unfortunately, this straightforward average equals 0, but we can square the argument that's averaged over. And this quantity is the Fisher information. Again, loosely speaking, the average amount of information we obtain per trial about the parameter that interests us. Now let's take one step beyond the Fisher information. We said that this distribution of the possible outcomes results from some measurement of the quantum state, but I never specified how we should measure the quantum state. We would like to maximize the fixture information over the possible measurements we could perform. I'll represent a measurement with this symbol. But we should actually make our measurement, our outcome probability, a function not only of the parameter, but also of the measurement we perform. Now I've taken the Fisher information that we saw on the last slide, I've made it a function of the measurement we perform, and I've maximized it over all possible measurements. This quantity is denoted by IQ. It's called the quantum Fisher information. It's the quantity that will interest us. Let me assume now that this Hermitian operator A that generates the U of theta that imprints the parameter on our quantum state isn't totally degenerate. Some of its eigenvalues differ. How come? We can see why this assumption is necessary and reasonable by considering how high the quantum and Fisher information can climb. Let's do the simplest thing we can imagine in our experiment. Let's send into our device a quantum state that's an eigenstate of this generator A. So when big A acts on the state, then the eigenvalue will result. This choice of initial state is problematic because the parameter theta will be imprinted on the state only in an overall exponential. When our operation acts on our inputted quantum states, it acts as this exponential, as we agreed. And because of the eigenvalue equation, this simplification happens. We call this E a global phase, and it can't be detected directly by experiments according to what we know about quantum theory. Instead, we want to imprint theta on our quantum states in a phase that we can actually measure. So what if we, in a sense, go to the opposite extreme of just inputting one eigenstate of the operator A? Let's input into our experiment a superposition of an eigenstate associated with the maximum eigenvalue of big A and an eigenstate associated with a minimum eigenvalue. This quantum state will transform via our device into this quantum state, which has an exponential here and an exponential here. We can pull out this exponential so that this exponential is left in between these two eigenstates. This exponential is called a relative phase, and it can be measured directly. Moreover, since this argument is as large as possible, this exponential can be measured easily. And so theta can be inferred easily. If we prepare this state and send it into our experiment, the quantum Fisher information, the average information we learn about the parameter, is 4 times the variance of A, or this gap, A max minus A min squared. We've said quite a bit about ordinary quantum metrology. Let me add one step to our metrological protocol. It's called post-selection, or throwing away of some of our trials. Why would we want to throw away some of our trials? Good question. So this experiment will now involve our inputting some quantum state. The device will operate on our quantum state and imprint the parameter on the state. Then we perform the post-selection step. We perform an intermediate measurement on our quantum state. This measurement is of an operator F. F is a projector, so it has 2 possible eigenvalues, or 2 eigenvalues, 0 and 1. If our measurement yields the 0 outcome, then we throw away our trial and start afresh. If the 1 outcome obtains, then our quantum state is projected onto some subspace, which I'll call F post-selected, of the Hilbert space. Also, once this happens, we should complete the trial and perform our final measurement. Again, we'll get some outcome little b distributed according to a probability distribution. Why would we want to do this post-selection? Why would we want to throw away some of our trials? Suppose that our quantum system that we input into the experiment is a photon, particle of light. Photons are detected by photodetectors. Photodetectors have dead times. Once a photodetector detects a photon, then it needs to take some time to reset. And during that reset period, it can't detect any more photons. So we might want to avoid overburdening our photodetector. We might not want to cause the photodetector to miss any important photons. So we should have the photodetector act only on the photons that we can tell carry a lot of Fisher information. How do we tell which photons carry a lot of Fisher information? Or actually, first, what measure should we use to identify how much information we're getting from the average completed trial? We'll use the post-selected quantum Fisher information. When we perform our post-selection measurement, the post-selection has some probability of failing, of yielding the undesirable answer, and some probability of succeeding. The success probability is this object, which again, if you're not familiar with quantum theory, might look a little bit mysterious, but it's just the results of some matrix multiplication. Once our quantum state is post-selected, it comes to be in this new quantum state. And actually, so this is a form that we can calculate for the quantum Fisher information, the average amount of information we obtain per successful trial. Don't worry about the mathematical form of this equation. It doesn't really matter, but the key property is there is some known form for the quantum Fisher information, and we can use this formula to find a nicer form for the quantum Fisher information expressed in terms of a Kirkwood-Dirac quasi-probability. Post-selection can increase the amount of quantum Fisher information we get from a successful experiment. Here's a really, really simple story that explains why in a classical, not quantum setting. Suppose that our inputs into our experiments are stars, blue stars or red stars. Our device, when given a blue star, rotates it through an angle theta. Our final measurement is how much the star has rotated. If a blue star enters the experiment, then it'll undergo the rotation and we'll obtain useful information about the parameter theta. If a red star goes through the experiment, then nothing happens to it, so we won't obtain any useful information. Therefore, it makes sense for us to perform post-selection before the final measurement. We can measure what color the star is. If the star is red, we should throw away the trial and start again, stop wasting our time. If the star is blue, we should perform the final measurement and we'll learn about theta. In this case, the post-selected information we learn is greater than the non-post-selected information we learn, because if we post-select, then we don't bother with any trials that provide 0 bits of information. Furthermore, this post-selection commutes with the rotation. Doesn't matter if we perform our sorting process after the rotation or before the rotation. Those two possible orderings would have the same effect. But again, the fact that operators can fail to commute with each other is very important in quantum theory. So we should ask what happens, for example, in a quantum setting, if the post-selection and in the rotation don't commute with each other. That question motivated this paper, which has two main results. First, suppose that the generator of the rotation commutes with the post-selection operator. Then the amount of information we get from the average post-selected trial is no better than the average amount of information we get from an ordinary trial in the absence of post-selection. So post-selection doesn't buy us anything. We could just prepare a better input state and perform just as well as we could with post-selection. The key to this proof was taking this quantum Fisher information and rewriting it in terms of that favorite quasi-probability distribution, the Kirkwood-Dirac quasi-probability. I would be happy to sketch the proof. I originally had a proof sketch in this talk, but again, I realized that a number of people here aren't familiar with quantum theory, and I didn't want to throw too much at you. But I'd be happy to talk about it and show the role of the quasi-probability if you're interested. We also showed that the quantum Fisher information can be greater in the presence of post-selection than in the absence. And if the quantum Fisher information is greater with post-selection, then you can be sure that that is because the quasi-probability distribution has negative values or non-classical values. And from that, together with the properties we talked about way at the beginning of this talk, we can conclude that the rotation generator A fails to commute with the post-selection operator F. Again, the non-commutation of operators is a key feature of quantum theory. So we can conclude that the non-commutation of operators provides an advantage in quantum metrology and measurements. And we learned that from this quasi-probability distribution. And that is one of the reasons why I love this quasi-probability distribution. Now, I understand that I was given 40 minutes to talk, and I know we started a little bit late. Should I try to wrap up more quickly, given that we started a little late?
You have like more 10 minutes, so you can take it if 2 or more if you need.
Sorry, did you say I have 10 minutes or 2 minutes?
10 minutes.
Okay, thank you. You might notice a problem with this scheme. When we perform our post-selection measurement, we have some probability of obtaining the outcome we like and we finish the trial, but we have some probability of obtaining the undesirable outcome. The probability of succeeding in the post-selection might be low, so we might have to wait a long time for a trial to succeed. However, every operation in the experiment has some cost. We're interested in experiments in which the final measurement costs the most. For example, I gave this illustration of the saturation time of a photodetector. So the quantity that really matters to us is the information we obtain about the parameter per unit cost. That's the information we obtain from n trials divided by the cost of n trials, which basically equals this fraction. The information obtained from n trials is proportional to the number of trials. It's proportional to the probability that a trial succeeds, and it's proportional to the average amount of information obtained per trial. The total cost of n trials is also proportional to the number of trials. This total cost equals the cost of the preparation procedure plus the cost of the post-selection plus the cost of the final measurement times the probability that the measurement succeeds. We're assuming that the cost of the final measurement is much greater than all the other costs, so we can effectively neglect these two C's. Our fraction simplifies. It simplifies further. And the information per unit cost turns out to be independent of the probability that the post-selection succeeds. In conclusion, the post-selection step can increase the information cost rates, which really matters to us, regardless of the probability that the post-selection succeeds. The theory that I just showed was recently realized in an experiment in Ephraim Steinberg's lab at the University of Toronto. They used a photonic platform. They not only confirmed the theory that I just showed, or showed that it appears to work in the lab, but the lab also prompted an extra theoretical discovery. We found that the quantum Fisher information, the average information we obtain from a trial, is proportional to how non-classical our quasi-probability distribution is. This was a fun back and forth. We expected the experiment to be just straightforward, a check of the theory, but it fed back on the theory and prompted us to figure out this proof. But these results might prompt some questions. We showed that if post-selection lets you perform better in metrology, then we know it's because the quasi-probability can go negative. Is the converse true? Does negativity of the quasi-probability imply you can obtain an advantage in metrology? The answer is no, and that was a bit unexpected. And furthermore, we saw that if the quasi-probability distribution is non-classical, has negative or non-real values, that's because some of the operators fail to commute with each other. Again, is the converse true? Does non-commutation of operators imply that a quasi-probability distribution defined in terms of them is non-classical? Again, the answer is no. And this answer turned out to be surprising because there were a number of people in the community who expected that the answer would be yes. And the proof is in this foundational theoretical mathematical paper. It's also interesting to ask, suppose that we have some Kirkwood-Dirac quasi-probability distribution or some generalization thereof. How much non-classicality can it have? How negative can it go? And how much non-reality can it have in it? We bounded the non-classicality in this paper. This work suggests an opportunity for future research. It kind of suggests mindsets or a toolkit. Anytime it seems that non-commutation of operators might be necessary for some quantum phenomenon to happen, we can check. We can try to look for some physically relevant quantity, like the quantum Fisher information. Try to decompose that quantity in terms of a Kirkwood-Dirac quasi-probability. Next, assume that all the operators involved commute with each other. The quasi-probability will reduce to an ordinary probability. Then we can use the axioms of probability theory to bound the physically relevant quantity. Then, suppose that the operators can fail to commute. We might be able to prove that the bound can be violated. So we can conclude that whenever one observes in physical world a violation of this bound, it's because operators fail to commute, as again is so important in quantum theory. So some settings in which this strategy might be employed include quantum computation and quantum error correction. In summary, we were introduced to the Kirkwood-Dirac quasi-probability distribution, which is my favorite representation of a quantum state. This quasi-probability distribution, unlike ordinary probability distributions, can become negative or non-real. We found that negative values of this quasi-probability underlie an advantage offered by post-selection, throwing away trials in the theory of measurement. We were able to prove that by using this quasi-probability. That result was realized recently in a photonic experiment, and one can take the strategy used and apply it to many different areas of quantum theory. Thanks for your time.
Okay, thank you. Well, now it's time for the questions. For those that are participating in the Zoom platform from abroad, you can raise your hand or place your question in the question and answer section. For those that raise your hand, we can give you permission for talking, so you can participate directly if you want. First, here in the auditorium is somebody that has a question for Nicole. Okay, please, can you help us with the microphone? Thank you.
Hi, I would like to thank for your nice talk. I love it. And secondly, I was wondering what was the hardest part you have working on?
You said, what was the hardest what that we've been working on?
Yeah, the hardest part you have been working on.
The hardest part of the research I just presented?
Yeah.
I think making the initial connection to the quasi-probability. It's actually kind of funny how these results came about. So I found myself kind of forced to define a generalization of this Kirkwood-Dirac quasi-probability because of a problem I was working on in quantum thermodynamics and black hole physics. I was trying to prove an equation, and I found that I could prove an equation only if I wrote down this funny looking quantity. And it turned out that this quantity was a generalization of this quasi-probability distribution. So one day I was presenting about this quasi-probability distribution to a group of string theorists who study black holes. And in the audience was a postdoc who worked on metrology, which I had never worked on before. He said, I've been working on this metrology problem for a while, and I think that your quasi-probability distribution is just what I need. Would you collaborate with me? And I, again, didn't know anything about metrology, but I said, sure. So I taught him about this quasi-probability. He taught me about metrology, and we found that that link was what we really needed to solve this problem.
Okay, well, thank you.
Thank you. Any other question?
Yes, yes. Yes, thank you. Nice talk. My question is about if we want to start to study quantum information, what literature do you suggest us to start to learn this topic?
My favorite textbook on quantum information is, I will type it in the chat so that hopefully you can see it. It's by Nielsen and Chuang, by Michael Nielsen and Isaac Chuang. I really like this book because it's pretty thorough and it provides physical intuition, but also quite solid mathematics. I'm not sure about the backgrounds of all people here, but this book is good for physicists. If you have more of a computer science point of view, then there's another book by Kay, Laflamme, and Mosca that might suit you better.
Okay, thank you very much.
Thank you. There's also a question from the people that is connected. The participant asked if the speaker can mention some real-world applications that can be currently handled with either our current quantum knowledge capabilities or her current research.
Yeah, I can share some slides about the experiment that was done based on our theory. I need to open a different talk that has some bonus slides. Here we go. I'll share my screen again. In this photonic experiment, the experimentalists had a photon that was polarized vertically. Light can have one of two possible polarizations, such as vertical or horizontal. And I'll label this vertical polarization with the 0 that we saw way at the beginning of the presentation. And this photon was acted on with this operation, which depends on the Pauli X operator, which is a 2x2 matrix that has ones on the diagonal, zeros on the diagonal and ones on the off diagonal. This photon ended up in this superposition of the states 0 and 1. There was an amplitude of cosine theta on the cosine theta over 2 on this part of the states, and an amplitude proportional to sine theta over 2 on this part of the state. Now this, remember, we said that the expected value of theta is 0, so theta is really small. We can Taylor approximate the cosine and the sine. This approximately equals theta squared over 4, which is really, really, really small. And this, however, is proportional to theta. So this is the term that carries information about theta. So we want to kind of amplify this term. We did so, or the experimentalists did so, by using this kind of a post-selection procedure. So they acted on the states with this, something that's very nearly a projector. So if loosely speaking, we could think of our photon as being in this state or in this state. If the photon was in this state, then it was very nearly killed off. Very, very little of it was let through the post-selection. But if the photon was in this one state, then all of it was let through. So this part of the state was amplified. We call this partially polarizing filter. And we can refrain from worrying about the technicalities here. After this step, which acts like the post-selection, they performed their final measurements, which is of whether the photon was vertically polarized or horizontally polarized. Because this detector over here, being a photodetector, would saturate. It would have a dead time. It would need to reset after detecting a photon. So with this attenuation, we decrease the number of photons that actually reach the photodetector. In this way, we spare the photodetector from having to detect much, but we still get a lot of quantum Fisher information per unit cost of the experiment. This was a first experiment based on our theory.
Thank you very much. Well, if there's another question here in the auditorium, please.
Hi, thank you. Well, I'm not very familiar with the quantum calculations, but I wonder how different is this from some results about sign measures? Because, for instance, in measure theory, you can have like measures with not necessarily between 0 and 1, but also you have some results of sign measures. And how different is working with these quantum calculations from, well, just a general framework with the sign measures?
Signed, since I'm having a little trouble hearing, is that SIGNED? Is that the word you were saying? I just didn't hear very well.
Sign, yeah, your measures with the sign, like could be positive, either positive or negative measures. So how different is this from some general theory using measures that not necessarily are positive?
I'm not familiar with that theory. So I'd be glad to learn more. Here, these quasi-probability distributions, or if you have a quasi-probability distribution, then it satisfies most of Kolmogorov's axioms. It just has to violate at least one. Different quasi-probability distributions can violate different axioms. So there's, for instance, a very well-known quasi-probability distribution called the Wigner function. It's famous for being able to go negative. And sometimes its negativity signals that there's true non-classicality, some physics that can really never be realized with classical mechanics. And I like this Kirkwood-Dirac distribution in part because not only can it go negative, but it also can be non-real. And non-real values of it signal a different type of physics. It's related to Heisenberg's uncertainty principle, that if you measure a quantum system, if you measure some observable of a quantum system, you disturb another one of its observables.
Thank you.
Well, thank you very much. We have no time for extra questions, but if you send us, we can send to Nicole all your observation questions and congratulations. Well,
Thank you for hosting me.
It's time to give to Nicole her award for this participation. Later, we are
thank
going
you
to
very
send
much.
you by email. But we are really glad of having you here and giving us this excellent talk about non-quite probability. So thank you very much.
Thank you for inviting and hosting me.
Thank you to everybody.